Hello, my dear friends. Myself is Dr. Vadiraj Tangur, Assistant Professor, Sri Jagadguru Tontagarya Government First Grade College, Mundaragi. So, in this video is a lecture series of Maxwell's thermodynamical equations. Among that, this is my second video. This is a video is concerns to BSc program of physics subject, second semester CBCS syllabus, and the paper is thermal physics and fluid mechanics. And learning objectives of this session is to know the concept of Maxwell's equations, to understand the meaning of all terms involved in the Maxwell's equations, usage of laws of thermodynamics, and session outcomes are knowledge of Maxwell's thermodynamical equations, understanding of each terms in the equations, usage of laws of thermodynamics, and prerequisites of this discussion is concept about first law of thermodynamics, concept about second law of thermodynamics, and partial differentiation. And syllabus prescribed for this chapter is Maxwell's thermodynamical relations with derivation, applications of Maxwell's thermodynamical relations to derive Clausius-Clapeyron-related heat equation, and Joule-Thomson expansion. And in my first video, I have derived generalized thermodynamical equation as dou T upon dou Y, keeping x as constant, into dou S upon dou X, keeping y as constant, minus dou P upon dou Y, keeping x as constant, into dou V upon dou X, keeping y as a constant, is equal to dou T upon dou X, keeping y as a constant, into dou S upon dou Y, keeping x as constant, minus dou P upon dou X, keeping y as constant, into dou V upon dou Y, keeping x as constant. To remember this generalized formula is like this: TSPV LHS, TSPV with a partial differential. Similarly, RHS is also TSPV. And in the denominator, if the LHS is of the form of sequence is of the form of dou y dou x, dou y dou x. RHS reverse, it is dou x dou y, dou x dou y. And whenever the denominator is dou y, keep the constant to be opposite, that is x. Dou x, then keep constant as y. Therefore, generalized thermodynamical equations can be said like this: dou T upon dou y, keeping x as constant, into dou S upon dou x, keeping y as a constant, minus dou P upon dou y, keeping x as constant, into dou V upon dou x, keeping y as a constant, is equal to dou T upon dou x, keeping y as a constant, into dou S upon dou y, keeping x as constant, minus dou P upon dou x, keeping y as a constant, into dou V upon dou y, keeping x as a constant. So from this generalized thermodynamical equation, we will derive one by one equation keeping x and y as a independent parameters like this: pressure, volume, temperature, and enthalpy. Now for the first equation, I am taking T and V as independent variable. T is temperature and V is volume independent variable. Therefore, you can take x as T, y is V. Now differentiate the x, differentiate the temperature with respect to x. Therefore, dou T upon dou x must be equal to 1. And with respect to y, if we differentiate, there is no term of y, therefore dou T upon dou y must be equal to 0. Next is like this, reverse. dou v upon dou x, we are differentiating the y term, it is v, dou v upon dou x, there is no x here, it must be 0, dou v upon dou y is equal to 1. Substituting dou t upon dou x is equal to 1, dou t upon dou y is equal to 0, dou v upon dou x is 0, dou v upon dou y is equal to 1. In the generalized equation, we can write the generalized equation like this. We are writing generalized equation. Now substitute the dou t upon dou x as 1. So dou t, first if we take the first term, dou t upon dou y is there. So dou t upon dou y, the value is 0. So 0 into next term is multiplied, it becomes 0. Therefore first term becomes 0. Minus second term. Think of second term. Dou p upon dou y, no terms in the above. Dou v upon dou x is there. So dou v upon dou x is again 0. So this term is 0. Therefore, LHS totally becomes 0. Now see the RHS term. RHS term is dou t upon dou x upon keeping y as a constant. So dou t upon dou x is 1. Therefore, keep as 1. And to dou s upon dou y as it is. I can write like this. Dou s upon dou y, keeping x as constant, it is minus dou p upon dou x, no term, dou p upon dou x, but dou v upon dou y is 1. So 1 into dou p upon dou x is 1. Therefore, it is minus sign. Therefore, we are equating here. Therefore, dou s upon dou y, keeping x as constant, must be equal to dou p upon dou x, keeping y as a constant. Now, in this term, replace x by t, y by v. Therefore, dou s upon dou y is dou v. Therefore, dou s upon dou v, keeping x is temperature T, is equal to dou p upon dou x. X is T. Therefore, dou p upon dou t, keeping T, keeping v is volume as y is constant. So this is first equation, first Maxwell's equation. But we know second of thermodynamics as ds is equal to dh upon t, or ds is a complete differential, dou s is partial. Almost if we make them equal, and we can replace dou s as dou h upon t, therefore it becomes dou h upon 1 into dou v upon dou v is equal to dou p upon dou t. That t terms goes to the right side. Therefore, equation we can write it as dou h upon dou v, keeping temperature as a constant, is equal to the denominator, it is h, that the denominator t will be goes to the right side numerator. Therefore, t into dou p upon dou t, keeping volume as constant. So this is first Maxwell's thermodynamical equation. Next, we will derive second thermodynamical equation. Look here. Now we can take the terms temperature and pressure as independent variables. Therefore, x is T, y is P. Again, differentiate T with respect to x and T with respect to y. Like this. Dou T upon dou x is 1, but dou T upon dou y is 0. Similarly, we can differentiate the second term, y is equal to p. That is, it is dou p upon dou x is 0, dou p upon dou y is 1. Substitute these four values in generalized equation. This is generalized equation. We should be substituting here. Look here. The first term, dou t upon dou y is there, but dou t upon dou y value is 0. Therefore, 0 the next term is 0. Now take the second term. Second term is dou p upon dou y. Dou p upon dou y is 1. Therefore, minus 1 into dou v upon dou x. Therefore, minus dou v upon dou x, keeping y as constant. Minus dou v upon dou x, y as constant, equal to RHS. We are coming to the RHS. In the RHS, dou t upon dou x is 1 and into dou s upon dou y. Dou s upon dou y, keeping x as a constant, minus dou p upon dou x is 0. Next RHS another term is 0. Therefore, remaining terms are minus dou v upon dou x, is equal to dou s upon dou y keeping x as constant. Here we will resubstitute x and y as x as t, y as p. We can write it as like this. Dou v upon dou t keeping p is constant is equal to minus dou s upon dou p keeping t is constant. Again, we know the second law of thermodynamics as dou s as ds as dh upon t. We can resubstitute here. Dou h upon dou p is equal to minus t into dou v upon dou t keeping pressure as constant. Therefore, this is second Maxwell's thermodynamical equation. Now, to third thermodynamical equation. Third thermodynamical equation is taking s and v as independent variables. X is equal to s and y is equal to v. Now differentiate. Dou s upon dou x becomes 1, dou s upon dou y becomes 0, and dou v upon dou x is 0, and dou v upon dou y is 1. Substituting in generalized thermodynamical equation and substituting the values, we got dou t upon dou y keeping s as constant equal to minus dou p upon dou s keeping s as constant. And we know second law of thermodynamics as ds is equal to dh upon t. Substituting here, dou t upon dou v is equal to minus dou p upon dou h keeping volume is constant. So this is third Maxwell's equation. Thank you for hearing with your patience. Thank you, one and all.